Hello friends. Now that we are done with solving partial differential equations of type 1 and type 2, let us see how to solve a partial differential equation of type 3. Okay, let us see that this is an auxiliary equation of a given partial differential equation like dx by p equals dy by q equals to dz by r. If we choose some multipliers like p1, q1 and r1 such that p1p plus q1q plus r1r equals to 0. Okay. Now the ratio gets converted into p1 dx. See, what we are doing is that we are multiplying numerator and denominator of the ratios by the same number and adding to the other ratio. So here it will be p1 dx upon p1p plus q1 dy plus r1 dz upon q1q plus r1r. Okay. Now what I am saying is that in this particular ratio, this bottom term, if it is equal to 0, then this numerator should also be equal to 0. And this particular term will be integrable if we choose P1, Q1, R1 in the simplest forms, which will be integrable. We will look this through an example. Okay. Let us say we have an example where we are asked to solve mz minus ny into P plus nx minus lz into Q equal to ly minus mx. If you see here, this is in the form of P into P plus some Q into Q equals to R, where P equals to this particular term, Q equals to this, and R equals to this. So we write the auxiliary equation as dx by P equals to dy by Q equals to dz by R. Now, if you see here, we have z here, y here. So x is absent. Okay. X here, z here, y is absent. Y here, x here, z is absent. So just by symmetry, if I multiply this by x, this by y, and this by z, and add this, what will I get? See, I have multiplied first ratio by x, second by y, and third by z. And once we add them, see, x into mz, and here we have z into minus mx. So it is minus mxz, and here we have plus mxz. These two will get cancelled out. Then x into ny, that is minus nxy, and here we have plus nxy. These two will get cancelled out. Then we have minus lyz, and here we have plus lyz. These two will cancel out. So the denominator we have as 0, while numerator we have it as x dx plus y dy plus z dz equals to 0. Now if we get what we say ratio in this form, we can directly say this is equals to 0 for the ratio to hold, or by other method, just cross multiply. Okay, so we get it x dx plus y dy plus z dz equals to 0. Once we integrate it, easily integrable, we get x square by 2 plus y square by 2 plus z square by 2 equal to sum c1 dash. And once we multiply this bottom 2 to the right side, here we will get 2c1 dash, which I am saying it as c1. Okay. Now, if we observe this again, let us see. Earlier we observed as we have zy, we don't have x. We have xz, we don't have y. And we have yx, and we don't have z here. Similarly, see, we have m and n, but we don't have l here. N and l, we don't have m here. L and m, we don't have n here. So what if I take multipliers as l, m, and n? See, multiplying, taking l, m, n as multipliers. Again, if you multiply these three, denominator will be 0. Okay, and we are left with lx plus my plus nz equals to 0. Now, once we integrate lx plus my plus nz equals to 0, we will get as lx plus my plus nz equal to 0. Just a slip of tongue. I want to say ldx plus mdy plus ndz equals to 0. We will integrate and we get this. C2 is a constant. And again, we will write solution in the form of phi of C1 comma C2 equals to 0, which is x square plus y square plus zx square comma lx plus my plus nz equal to 0, where phi is an arbitrary function. Then this is how you solve partial differential equation of type 3. Okay.